Okay. The shell method is an alternative method for finding the volume of a solid of revolution. It's also known as the shell method because it uses cylindrical shells. And in this example, where the shell method is being used, W represents the width of the representative rectangle still. So it's like it's still either delta X or delta Y. The H is the height of the representative rectangle. And notice how the representative rectangle is parallel to the axis of revolution, which is different in the disk and washer method. So, the outer radius of this figure is P plus W over 2. And remember, P is the distance from the axis of revolution to the center of the representative rectangle. And then the inner radius, which accounts for this whole part, is P minus W over 2. And this is the radius from here to the inside of the representative rectangle. So in other words, the volume of the shell is equal to the volume of the cylinder minus the volume of the hole, and the volume of the cylinder is pi r squared h. So in this case, R for the cylinder is P plus W over 2, and then the radius of the inner hole is P minus W over 2. So that's where it comes from, and then when you simplify, you get 2 pi ph W, and then it's also just 2 pi times the average radius times the height times the thickness. And then the equation for the rectangle, or delta V, is just 2 pi times P of Y times H of Y times delta Y. So then the volume of a solid is just equal to the integral from A to B or C to D of the height, the radius, which is the distance from the axis of rotation to the center of the representative rectangle, times the height, dy, and take the integral of that. And then it's written on this next page. So here are the two equations, depending on which axis is the axis of revolution. In this one, the horizontal axis is the axis of revolution. So in this one, notice how you're using P of Y. Your equations are should be in terms of Y, because that is the height. And then in the vertical axis of revolution, your term should be in terms of X. And because the height is this way. Okay, so let's try a practice problem. Let me get this standing. Okay, so let's try a problem. Say we have y is equal to x cubed and x minus x cubed, and it's bound by the x-axis, so this is my graph, and you're rotating about the y-axis. So first thing you need to do is sketch the graph, which I did here, and then next you need to draw your representative rectangle, and since we're rotating about the y-axis, the representative rectangle must be parallel to it, so that's why it's parallel. And then this is going to be delta x, and this is going to be h of x, or the height of the rectangle. And the height of this is just going to be x minus x cubed, so h of x is equal to x minus x cubed, and the axis of revolution is just x is equal to 0. Oh wait. Yes, this is the height of the rectangle. You would still subtract it from here because it's this direction. So since this is still y equals 0, then you subtract 0. So your height is just x minus x cubed. So this is equal to our h of x, and then we need our p of x. And our p of x is the distance from here, from the axis of revolution, to the center of the representative rectangle. And this value is always going to be x in this case, because the axis of revolution did not shift. If it was the opposite direction, so say it was turned this way, then this would be y, and this would be delta y, of course. But since it's in this direction and delta x is in this way, you have to use x. So say, hypothetically, if this was shifted over to the left 1 unit, then you would do x minus negative 1, and you get x plus 1. So the distance from that negative 1 to this position would be x plus 1, which would make sense, because if you had negative 1 here and this position is 1, then the total distance from negative 1 to 1 would be 2, so x plus 1, 1 plus 1, 2. And that's just an easy way to remember it, and it should logically make sense too. So our p of x is x in this case. So then we can set up our integral. So another thing about the integral is don't be confused about where the integral should be. It should still be from 0 to 1, and it should not be from here to whatever this y value is. Because if you think about it, when you're rotating the shell, this is the radius that's gonna progressively change a little bit at a time. The h of x, that's the height, so that's gonna change on its own. So this is what you're adjusting, and this is kind of like the accumulation, integration as an accumulation function. You have to change the radius of this shell. So, forgot to write the equation. The equation for shell method is volume is equal to 2 pi from a to b of p of x times h of x. So volume is equal to 2 pi from 0 to 1 of p of x, which is x. H of x is x minus x cubed. I forgot the dx. Okay, so I was saying, I forgot the dx. So after you get the original equation, you can start substituting them in. So v is equal to 2 pi, the integral is from 0 to 1, and p of x is x in this instance, and then h of x is x minus x cubed dx. So then you can multiply out the x, so you get 2 pi, the integral from 0 to 1 of x squared minus x to the 4th dx. Take the integral, 2 pi is 2 pi times x cubed over 3 minus x to the 5th over 5 from 0 to 1. And then 2 pi times 1/3 minus 1/5 minus 2 pi of 0 cubed over 3 minus 0 cubed over 0 to the 5th over 5. And this all goes to 0. So then you have 2 pi times 2 over 15, which is equal to 4 pi over 15. And this is the volume of this equation in the x-axis from 0 is less than or equal to x is less than or equal to 1. Rotate about the y-axis using the shell method.